Hi friends, today on 1 Minute Math we're going to be talking about graphing sine functions. So what I mean by that is like f of x equals sine x or y equals sine x. We're going to try and imagine what a graph of that looks like on the xy coordinate plane, and we'll also look at some transformations of them. Ultimately we want to be able to graph any kind of function f of x that would look like a, some number a, times the sine of some number b times x minus h and then plus k. Those are all the transformations we're going to look at. Hopefully those are familiar variables that you use in transformations of other functions, and so this can just be an extension of that. But let's not get ahead of ourselves. We're going to begin by looking at what it means to actually graph the sine function. This can be a little bit mind-bending, because when I say something like y equals sine x, okay, we've got lots of different pictures going around in your brain. Hopefully when you think of the sine function, there's one part of your brain that's thinking, oh, this is SOHCAHTOA geometry. Sine is opposite over hypotenuse. And then this x is that angle, and y, who knows what y is, right? Okay, so another part of you is thinking about this unit circle. You've seen this before, where when I go around the circle, the y coordinate of this point gives me the sine value of that angle. So the coordinates of any point here would be cosine theta comma sine theta, where the point meets, the angle meets the circle. And now we're talking about y equaling sine x when x is cosine, and like we've got x's and y's floating around in a lot of different contexts here. And it's just going to be uncomfy for a little bit. Sine isn't quite as bad as cosine. When we try and graph y equals cosine x, sometimes your brain can do all kinds of funny things and convince you that that's not a thing because cosine isn't y. In this context, though, when I'm graphing y equals sine x, the x is the input of the sine function, which is the angle. So the x, you'll notice that what I have drawn in red over on this graph on the right, this x-axis, this measures an angle. This is the x here is the input into my sine function, and it is indeed this value, that x radian measure of that angle as I go around the circle. So we're still going to be talking about x and y coordinates of this point where the angle meets the circle, but that's not the x coordinate that I'm going to put over on the right. So let's just see, we're going to plot a couple points here. As I begin, when I have an angle of 0, the sine of that angle is 0. The y coordinate there is 0. Excuse me. Let me just make a table of values for a little bit. X sine x. So my first point will be 0, 0. Loop. Then as I move this angle, as the angle grows, let's take pi sixths, right? And an angle of pi sixths, the sine of pi sixths, the y coordinate there is 1/2. So I'm going to have a point here at pi sixths, 1/2, right there. Let's go all the way up to pi thirds. We're going to skip over pi fourths just in the sake of time. And when I go up to that angle of pi thirds, now I have a sine of that angle is root 3 over 2, which is about 0.87. There's my pi thirds, 0.87. And then you kind of see where this is culminating as this angle goes all the way up to pi halves. The sine of that angle is 1, and that is indeed as high as it's going to go. So over here at pi halves, I get an angle of 1, which is just higher than 0.87, and that's going to be the maximum. As the angle continues to grow, as I continue to move this direction along my x-axis of my other graph, and my graph of my function, the y-coordinates begin to decrease. Right here I'm at 0.87 again, then down to 0.5, then down to 0. Let's plot those a while. 0.87, 0.5, 0. See this kind of smooth arc forming where the y coordinates go back to where we started. The y coordinates started at 0 and sped up. It very quickly got much higher and then kind of slowed down, still going up, but slower, levels off at 1 and starts decreasing slowly now, more quickly, bam, down to 1, down back to 0 at an angle of pi. And you can predict what's going to happen here as I keep going. As this angle grows, you see the y-coordinate getting negative, more and more negative until it bottoms out at -1, and then it gets closer to 0 slowly at first, then more quickly, and boom, by 2 pi, I'm back to where I started. So I have this same kind of arc happening on the bottom. That's at an angle of 2 pi. Leveling out, bottoming out at -1, just like it topped out at +1 on the top. This is a sine wave. You might have heard these graphs called sine waves or sinusoidal waves before, and you can see why. It's actually like a wave. And interestingly enough, if we kept going, I would have the repeating pattern. See, if this angle keeps on going around and around and around and around, the y-coordinate keeps going up and down and up down and up and down in this kind of unending way. Let's just take a graph for funsies. Let's look what happens if I graph y equals sine x here on Desmos. Bam. I get that wave form repeating infinitely in either direction. If I go in either direction, it just keeps repeating again and again and again. That's a sine wave. So some vocabulary here while we're in sine wave land. And then we're going to start adjusting it with some transformations. The height here, the mathematical term for that height, the distance from the center to the top, is the amplitude, A for amplitude. Just like an amp, an amplifier, if you plug in your guitar to an amplifier, the sound waves that are emitted have a higher amplitude. The horizontal distance from the beginning to the end of the wave, you would call the wavelength in certain contexts, and in other contexts we might call it the time period of the revolution, the time period of the pattern before the pattern repeats. So period is the word that we're going to use for that most often. Depending if you're in a physics context or a purely mathematical context, the words wavelength and period or time period they have slightly different meanings, but for our intents and purposes here in a pre-calc kind of context, we're just going to say period or time period, and that will be. So in physics, the symbol or the variable that we use for period is capital T because it's the time period, okay? But here in math, sometimes we just use P for period because we're used to using the same letter that the word starts with. So the period is a length. It's a horizontal length that marks the distance between equivalent parts of this wave. Basically measures how much wave you need until it repeats. It's a horizontal distance of a single wave. If we look over here at our graph, you notice 0 to 2 pi, that would measure that part, like the middle to the middle where it repeats, but it would also measure from the top to the top. That would also be a distance of 2 pi, or the bottom to the bottom. That would also be a distance of 2 pi. So as long as you're going from one point to another corresponding point on the next wave over, that's how you measure the period or the wavelength. And in this particular wave, we're starting at 0, 0. The average value of this wave is 0. That's the vertical value that represents like that straight through the middle of the wave. We're going to call that the average value. And if this wave were shifted to the left or right at all from where it started, we would call that the phase shift. I'll write phase shift on that formula when we see different ones. All right, let's start fiddling with the amplitude. If I wanted to make this wave twice as tall, hopefully you have an idea based on what transformations you've done of other functions. If I want to take these y values and just make them bigger in both directions, I would make it twice as much 2 times on the outside, 2 times sine x, and you see how that stretches my wave by 2. There's lots of explanations for why this happens, but probably the easiest one is simply that after I take the sine value, I multiply it by 2, so the output becomes twice as big. That means the positive y values get twice as tall, and the negative y values get twice as small, essentially, twice as far away from the x-axis. Let's just put another number on here to check our guess. What if I did 1/3? 1/3 sine x. Would you look at that? It's 1/3 as tall. Same wavelength, we're hitting the x-axis at exactly the same point, so it's got the same zeros, the same horizontal behavior. Vertically it has not shifted, but stretched. What do you think is going to happen if I put a negative on it? Oops. Did you predict it right? So a negative multiplies all the y values by -1, which just flips it right over the x-axis there. Let me compare to the original. The only difference between the red and the blue one here is that the blue one has been flipped over the x-axis. So this number that goes in front, we just call the amplitude, and I can put any value there I want. The positive or negative will determine whether it goes up first or down first. Let's get some space here. Y equals A sine X. The value of A determines how much distance there is from the center, from the average value, up to the top or down to the bottom. Very often your teacher will say something like, graph 2 periods or 2 waves, blah, blah, blah. So you have to keep it going for more than just that one wave. But the A here would measure this distance, just like we would have predicted from the word amplitude. The amplitude, the A measuring the height of that wave, is completely consistent with this. And if A is negative, we get this shape. Valley first and then mountain, instead of mountain first and then valley. Awesome. Let's go ahead and see how we can change the average value. Let's say that I wanted to take my sine wave here, and instead of having it be centered on the x-axis, what if I want this sine wave to be centered up here at y equals 5? Not any taller, still having a height, a distance from the center to the outermost points as 1. But with an average value of 5. Now it would be going between 6 and 4. Any guesses? If you guessed that we should add to our sine wave, then you guessed right. There he is. Okay. I have parallel waves. The size hasn't changed. I'm still doing nothing to the x. I've not stretched or shrunk it or moved it in any way horizontally. I've just moved it up vertically. For funsies, let's say I wanted it to go down 1. I could just put a -1 on the bottom or on the outside after the sine x. So this plus or minus k on the end, that k is exactly the average value. Okay, so let's practice one here. What if I asked you to sketch a graph of y equals 2 sine x plus 4? Most things in math work better if we start from the right and go to the left. So let's start with this. Average value of plus 4. So that means the middle of my wave will be at positive 4. Amplitude of 2. So that means the distance from the center to the top is 2, and the distance from the center to the bottom is 2. So I simply did 4 plus 2 and 4 minus 2. This gives me a nice little kind of horizontal area that I can put my wave in. And I know that my wave will go middle, up, middle, down, middle. Went up first because it's a positive amplitude. The whole wavelength is 2 pi. We haven't affected that yet. We're not doing anything to the x. So I can split up that 2 pi into fourths. That's often a handy way to label your axes. Then I just have to connect my dots. Ta-da! Let's do one more before we deal with the x. How about y equals negative 3 sine x plus 2. Going from right to left. 2 is the average value. 3 is the amplitude, so I'm going to go up 3, which would be 5. Up 3, which would be 5, and down 3, which would be -1. So there's my little range that I'm going to put my wave in. It is a negative amplitude, -3, so I'm going to go down first. Middle, bottom, middle, top, middle. That's 2 pi. Connect the dots. And there we go. Easy peasy lemon squeezy. If your teacher wants 2 waves, just put little tails on there and make sure you get 2 waves. Wonderful. Next up, what happens if we want to change what's happening to the horizontal, either the wavelength or where it starts? And I hope that you're familiar enough with function transformations that you know multipliers are how we change the shape, they're how we stretch things, and then addition and subtraction is how we move things. So if we go back and look at our original, like our goal equation here, we know what the A does, that's the amplitude. We know what the K does, that's the average value. And we've got 2 numbers left, the B and the H. One is times and one is minus. It should not surprise you that the B here, the times one, is going to be the one that affects the period. And it's not equal to the period, but it affects the period. Let's imagine, let's go back here. I'm going to erase some of this stuff. Actually, no. No, I take it back. I'm going to erase this. I'm going to erase my amplitude. I'm going to leave my original wave there, though. Let's say I want to graph y equals sine 2x. Okay. So I'm just going to put an intermediate step here on our column, on our table. If I was going to do 2x, so I put in x equals 0, I still have 0. 2x is 0. If I put x equals pi 6, now 2x is pi thirds. If I put x equals pi thirds, now 2x is 2 pi thirds. And if I put in x equals pi halves, now I'm looking at x equals pi. And the sign of those things is going to be vastly different. I jump all the way up to that 0.87 right away. And this 2 pi thirds is going to be 0.87 like over the hill after I go over the peak. And then by an x of pi halves, I'm plugging pi into sine and getting 0 again. What that tells me is that I've gone all the way up and all the way down by the time I get to pi halves. And really, I would only need to put in an x value of pi to complete the entire circle. Because if I'm multiplying my inputs by 2, then by the time I get to an input of x, I've actually given an angle of 2x. I've given an angle of 2 pi. Essentially, what that B measures is how many waves happen between 0 and 2 pi. How many waves between 0 and 2 pi. So perhaps a more practical way to think about this is that if we call that B, sine bx, P times B will always equal 2 pi. If I wanted to graph, all right, there's my original. If I wanted to graph y equals sine, let's say sine 1/2 x. Let's compute this before we look at it. Sine 1/2 x. That means 1/2 of a wave is going to occur between 0 and 2 pi, or P times B is 2 pi. The period I'm going to expect is 4 pi. I'm going to expect to see one wave take up a whole 4 pi on this x-axis. And there it is. Do you see how it got stretched out? What if I wanted to look at y equals sine 6x? I got 6 whole waves happening between 0 and 2 pi, where the period would be 2 pi divided by 6, or pi thirds. So it only takes until pi thirds before I complete an entire wave. All right, so that's the B. That's the B multiplier. That's probably the weirdest one because it's not, that number is not immediately apparent in the graph. You have to do some computation. I'm going to say P times B equals 2 pi. And all that leaves left here is the H. And H is a horizontal shift. In trigonometry land, we call that a phase shift. phase shift, I'm going to say slash horizontal shift. You will rarely see these. Okay. It's very rare that you have to put a horizontal shift on a sine graph for lots of reasons. I'm just not going to go into all the details of that right now. But let's put all this together. We're going to try one, and then we'll see if we're right. So let me put some numbers on. Let's just do the B and the H for starters. Sine 1/3 x minus pi. Okay. So I'm starting from the right and going to the left. My graph is going to start at a value of pi. Go, do, 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 do. That's where I start. And the period, p times b equals 2 pi. The period is 6 pi. So now I'm going to do a little computation. This whole thing is 6 pi, that distance. So if I start at 1 pi and I have distance of 6 pi, that ends me at 7 pi. Right? And I can connect my dots. And this was just a regular old sine wave. There was nothing unusual happening to the y values. There's no plus k at the end. There's no different amplitude. So it goes up to 1, down to -1. If you want to, like to find this middle value, you can always just do the average. Pi plus 7 pi divided by 2 is 4 pi. That's an easy way to find the point in the middle. If your teacher wants an x value for that middle point, finding the x values for these middle points when you have a phase shift can be a pain in the neck. All right, let's put it all together. We're going to graph y equals, let's make it negative. -3 sine 2x plus 1. Average value, 1. Period, 2 times b or p equals 2 pi, so p equals pi. Half of that will be pi halves. I can mark those fourths if I want to. The amplitude is 3, so I'm going to go up 3 to 4, down 3 to -2. Get my nice little column of where my wave lives. I'm going to go middle. It's positive, so up, middle, down, middle. Connect the dots. There we go. There's your wave. Easy peasy lemon squeezy, right? Let's check and see if we were right. -3 sine 2x plus 1. Looks like it. It's a little bit hard to tell. But yeah, there it is. Goes up to 4, down to -1. It did a valley first and then a mountain as a period length of pi. Sweet, we did it. Final thing here before we call it quits on this Zoom or on this lesson is to see what happens when I ask for cosine. So we were graphing y equals sine x here. If I make this sine a cosine, let me erase a lot. Actually, I'll just do this. Nope, I erased too much. If I make that sine a cosine, a few things are going to change. A few things are going to stay the same, but a few things are going to change. We know that cosine is the x value of the points on the unit circle. So I need to change how I'm looking at these things. This blue and that blue, they were representing the same quantity. They're not anymore. What's going to be my output values over on the right will be the x values on the left, not the y values. Y equals cosine x. The input x here is still the angle, but if I make my table, I'm just going to make a couple of points here, x cosine x. I start at an x value of 1, of a cosine value of 1. As I move around, the x value decreases. Like it starts at its highest value, and now the x is going to decrease slowly, then quickly at first, and then 0. So by the time I get up to pi halves, the cosine value is 0. Starting at 1, I went down to 0. And I immediately go negative, all the way down to -1. And if you're following along, you can see what's going to happen. I come back up, and by 2 pi, I'm back at a value of 1. Now, if I extend this, and we kind of squint our eyes a little bit, you're going to agree that this is really just a sine wave. It's just at a different place. If I graph, all right, there's my sine wave. If I graph y equals cosine x, it's exactly the same wave. It just looks like it moved over a little bit. In fact, it moved over pi halves. Those waves are now completely the same. This is one of the reasons why you don't often have a phase shift. Like when you're trying to graph a sine or a cosine wave, you can just choose sine or cosine and kind of put the starting point wherever you want it. But yeah, sine and cosine have the same properties, they have the same amplitude, they have the same period, so those features work exactly the same. It's just a matter of where you start your wave. So if I was asked to graph y equals 5 cosine of 1/3 x plus 2. I start this so much like I would start the sine graph. Starting at an average value of 2, up 5, down 5. So there's my little column. The period, p times 1/3 is 2 pi, so the period length here is 6 pi. So the middle would be at 3 pi. I've got my 4 points that I want to graph, or my 5 points I want to graph, but instead of going middle, up, middle, down, middle, I'm just going to start at the top, middle, bottom, middle, top. Whoop. And then keep going as long as you need to appease whatever the expectations on your assignment were. That is how you graph sine and cosine waves. I hope you found it helpful. Thanks for watching.